All right, here we are back again, second day. For today's class, we're going to start with just a little bit of continuing to introduce and refresh you on some of the material from 211, especially as it is relevant to what we're going to start doing within probably the first 10 minutes, which is get started actually live coding the linked list we're going to be using for the first assignment and for a good chunk of the quarter. Questions? Any questions at all about the class? Anything else before we get started? So we ended last class with this class exercise where we were going to do this. And let's actually take a look and think about this actual process, both from the perspective of a linked list and an array list. I'll use different colors on different days, and depending on what we do, I don't know if it says anything about my mood. I'm trying to figure that out. No, not really. Today is orange. I don't know why. So let's go ahead and do this from the perspective of an array. So we're going to start with an array. When you make an array list, whether this is known or not, I believe the default size in Java is 8. So if you make a new array list, it will come with 8 elements. And as you start inserting into it, it will expand or retract as needed as it starts to fill up or get empty as you need more space or it would rather save the space. We'll talk a little bit more about why that is in a second. Yeah, that's great. So, oh no. So we're going to assume we have an 8-position array to start. That's even enough. You will quickly learn I have the drawing skills of a second grader. Excellent. It leads to some very fun moments. So we want to insert 16 at the end. Right now, the end is going to be pointing at the 0th element. I can subscript this. 8 elements, 0 to 7 inclusive. We start with 16 at the end. That is the end as it exists at the moment. We're going to insert 9 at position 0. In order to do this, we need to now shift everything over, right? We can't insert 9 at position 0. That would overwrite it. We don't want to overwrite it. We want to insert it. Question?
Inserting 16 at the end. I thought it was at the end, so
it's the end of the existing array. Yeah, so we're going to insert it. Right now, there's nothing in it. So the end, you can think of the tail of a linked list might help you to visualize where the end of something might be. So we're going to shift over the 16, and that gives us enough room to insert the 9 at position 0. Next, we want to set the element at position 1 to 22. Set means to overwrite. So the 16 is going to go away, and we're going to replace it with a 22. We now want to insert 12 at position 1. To insert, we need to move everything to the right of it over to make space for it. So the 22 is going to shift position over here to index 2, leaving us space now for the 12. To insert 18 at the end, we need to know where the end is. You could always, with an array, query its dot length. Dot length will tell you where that is. This dot length would be 3. That tells us we want to insert at position 3. So we'll insert 18 at the end. That'll put us to there. Then we want to remove the element at position 2. To remove, we need to shift everything to the right of it over. So we are going to shift the 18 over, overwriting the 22. And get rid of the 18. So this would be our final list. Agrees, disagrees?
I'm a little confused on, so removed, you removed 18, and 18 was in position 3, right?
Was it?
Shouldn't you just move the 18 over to 2?
Did I say 22? Yeah, that's true.
Yeah. There we go.
That makes more sense. Trying to fool you on day 2. All right, so now let's do this exact same logic from a linked list. So thinking about this from a linked list perspective is going to be slightly different. We won't have to do quite as much of the moving over, but instead we're going to need to figure out, where does this node's previous now point? Where does this node's next now point? We'll start with a singly linked list because I think that makes sense. So the dot previous would only work for that. So we want to have a dummy head or not. Basically, there are the 2 different kinds of linked lists, whether there's a dummy head, whether there's not. I like to not have dummy heads, but we will be thinking about it both from that perspective and from not that perspective. So the head is really just a reference to a node. And as we start, that reference doesn't point to anything. Are we familiar with the concept of Java references? Objects that point at something like that. So right now, this is just a head is an integer that's going to tell us the location of where this is in memory. That's really the C way of thinking about it, but that's what Java is doing underneath the hood that you don't need to be aware of, but it's useful to be aware of because it will really help it make sense of what it's doing. So this is why you get something like a null pointer exception. When I say I'm going to assume that this head is a linked node of some kind. And I want to say, what is heads.value? I'm going to follow this arrow and expect there to be a node-shaped object here. There is no node-shaped object here. So it doesn't have value. No pointer exception. An arrow that points off into nothing. It's like saying the student that I am pointing to, answer my question. There's no student there, I'm going to get silence. If we insert 16 at the end, this is going to say, all right, let's make a node and make sure that our head points to that node. So now we can make a new linked node. I'm going to have a value and a next. The value is going to be 16, and the next is going to point off to nothing. If we were to query head.next.value, we get a no pointer exception because head exists, it has a dot next, we can follow that. That would be null, right? Head.next is null, it's not pointing at anything. But head.next.value or head.next.next, all of that last dot value and dot next assumes that there's an object here. There's no object here, we're going to get a no pointer exception. So this is the entirety of our list right now. We can query head, that gets us this node. Head.value gets us this 16. Head.next gets us null. Head.next.something crashes our program. All right, now we want to insert 9 at position 0. To do this, we basically need to modify the head in some capacity because we want to insert at position 0, that's going to be the new head of the linked list. So we're going to now make a new node. I do this kind of on purpose, making it point off here. What have I done? If I put 9 here and made a node with a next like this, I've lost the 16. What happens in Java if you have an object with no reference to it? Yes. Yeah, the Java garbage collector comes and sucks it up. So Java has a garbage collector. It's just a program that's running behind the scenes, and it's looking for any reference, any object that exists in memory with no way to get to it. And it's going to delete it because there's no way to get to it. It's lost in the abyss. So before we move this head pointer, I'm going to back up a little bit. We're going to make some variable that we're going to call something like 10. And we're going to point that at this, as this is still pointed at that. Now we have a reference, a way to reference this node. What's the first operation that we would want to do to make sure we can connect these nodes in a way that's going to have 9 in position 0 and 16 in position 1? What do we need to do?
We should make, 10 for the 9 nodes next value.
Yeah, temp dot next equals. Head. Head is the way to get at this node. So that would change this pointer to point here. Now. We can get at this node with 2 different names. We'll just call them names for the moment. We can say that gets us this node. Temp dot next now also gets us this node. I find it to be very useful to draw out these kinds of diagrams as you go. But do note that there's not necessarily a linear order to this. There is, once we redirect head, we can say now head equals temp. And when we leave that method, since temp was declared as a local variable, when you leave that scope, any names associated with that scope are going to go away. So this local variable will be deleted, but note that we don't need it anymore. Now, head refers to the 9, which is at position 0 in our list. Head dot next now points to the 16. So we've now emulated exactly what we did in ArrayLand. These also don't have to be stored in the same location, right? We know this about arrays versus linked lists, maybe. Arrays have to be stored contiguously. This means that our computer's memory can just be seen as one really, really, really long one-dimensional line of storage. Here's our computer's memory, all 16 gigabytes or 32 gigabytes or whatever it is, one long string of billions of addresses. This array needs to be stored contiguously in some chunk of that. This might be the space in memory that's storing this array. But this linked list does not need to be stored that way. This could be stored with a node over here, and a node over here, and a node over here, and a node over here. But the node that's in position 0 is this one. Doesn't matter. So some of the benefits of a linked list. All right, let's move on to the next one. So we want to set the element at position 1 to 22. If we're thinking about this in terms of code, great, we can go directly there. It just sort of reminds, sorry, in code we don't have a direct way to get at position 1. If we wanted to hard code that, we could say head.next. Or if we wanted to write a generic piece of code that could get us whatever is at position X, then we would have to write a loop that says whatever the value of X is, we need to start with the head and iterate some number of times going to the current nodes .next until we get to the index we are looking for. Unlike with an array, where we can just kind of jump there. The reason we can just jump there is because this is stored contiguously. Let's say that this is memory address 1000. We use low numbers because doing numbers too much larger than that is not fun. If I wanted to ask you, what is the value at position 5? What is the math that you could use to grab that without writing a loop? If you wanted to know the actual value at address 5, let's say that these are stored as integers and integers take 4 bytes. So this would be at memory address 1004. This would be at memory address 1008, 1012, etc. How do we get the value that's stored there? We have to go look up to what memory address. You take the starting address and add to it the size of an int. So we take this 4 and we multiply that by the number we want to get to. This tells us that, obviously, we do that first. We should look at address 1020. This is why it is so fast and easy to do array access. Or find in an array is because no matter where it is in that array, it is a multiply and an add, and you're there. And computers are very fast at multiplies and adds. They can do that almost instantly from our perspective. A linked list, on the other hand, doesn't have that kind of math associated with it. So we just have to write a loop and deal with how long that takes. All right, we wanted to set the element at position 1 to 22, so we're going to go into a loop, say head dot next, doesn't really matter how we get there, but we're going to change this 16 to be a 22. Great. Now we want to insert 12 at position 1. How we're going to visualize this is we now need to have a loop that goes to the position before we want, because we need to change this next pointer to be some new node. Well, we know that we want to insert a node that is 12. So I'm going to make another node. I'm going to assign it the value of 12. Right now this points off to nothing, and we'll just call this 10. For now, that's the way we're going to access those. So to insert something at position 1, we first need to know what is at position 0, the element before it. Because we want to modify this next pointer to point at this. But again, if that's the first thing that we do, we're going to be in trouble. Why is that? Yeah, we don't have any way to reference this next, whatever comes next in this entire linked list. We're going to chop off the linked list right there. So the first thing we want to do to make sure that this is going to work is we want to change this next pointer to point there. That has to happen before we modify any of this connection. Think of it like a snake. You're chopping the snake's body in half. You need to know where the second half is, but I don't know why I like violent examples so much. All right, so this is now going to point also to this node. And now we are free to modify this to point here. So instead of this node pointing there, this node will now point here. When this method ends, this temp will go away, and now we have a nice snake of a linked list that starts. Here's the head. We have 9, 12, 22. We now want to insert 18 at the end, assuming we had a tail that could get us directly here, or if not, we could go until the current nodes dot next is null. That would be the other way without a tail to figure out where this list ends. We can now insert 18 as another new node that goes there. Great. Now to remove the element at position 2, we would go into a loop. 0, 1, 2. To remove this node, all we have to do, we want to again know the node that is before it, so we make the connection that skips over that. As we do this, as we redirect that pointer to point there, there's no reference to this node. We can't get there. So the Java garbage collector will come eat it. Question?
So when you kept adding a new node, like to the list, you kept creating a temporary dummy head.
Yeah.
That points towards that node.
Yeah.
Is there an advantage to doing that? I mean, you can just create a node itself and then add it to the list. Why did you do it that way?
Yeah, so it's mostly just to show how all of that works. You can directly create the node, and you can one line it.
Or you don't have to put a dummy head.
Right. Right.
Okay.
So the temp itself is not a dummy head. The temp itself is the name of the variable as you make that new node. So the difference is just a matter of whether you say this dot next equals new node, blah, 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 that makes the node and assigns this next pointer to it, or whether you take two lines and say node temp equals new node and make the node, and then say something that some other variable dot next equals temp.
Okay, so the temp is just the variable name.
Yeah, and you'll see that for any object. You can do this for any object. An object is really just an integer reference to the place that that object is stored in memory. You can think of it as this is a memory system, and if I wanted to access a student stored at a particular location in the classroom, I could have some variable, some piece of memory that says that student is stored there. That piece of memory would not necessarily refer to the person object, but it refers to the location. If you get up and move, I'm still pointed at the location, I'm not pointed at you. So yeah, these variables are pointed at the location where something is stored. It's just that the location isn't changing. Great question. So, all right, we've gone through this in array form, we've gone through this in linked list form. Anyone have any questions about either of these walkthroughs? I do this before diving into the code because we're going to be writing code that matches this logic. So we're going to be coming back to these kinds of diagrams and drawing and redrawing arrows to make sure that we are writing the correct code. Other quick points before we get started. We talked about how it didn't really matter whether you thought about this as an array list or a linked list. That's because of this concept of an abstract data type. An abstract data type is just a list. Lists can all do the same subsets of things. Yet, the underlying implementation of the different kinds of lists is different. But from the end user's perspective, it doesn't matter whether they use an array list or a linked list. They can still instantiate one or the other, and they can each do the same subsets of things, although differently. So you can see that if we actually go to the Java documentation, we can actually see that this is what the list interface looks like. This is going to be important to us because we are going to be rewriting Java's linked list, making our own linked list. So to do this, we might want to make our own interface. If we make this our own interface, then we could start to make different kinds of lists that can all do the same thing. This ends up being useful when you want that functionality to be interchangeable. Have a user be able to instantiate one or the other and do the exact same subsets of things. So if you have not seen or used the Java documentation like this, incredibly useful. You can see exactly what all lists are able to do. If anything implements list, which array list does and linked list does in Java, then you see that you can add at the end of the list. You can add at a specified position in the list. You can add all, taking any other collection and put it in the list. Now, a collection is more abstract or vague than a list. A collection could be a set. It could be, there are many different kinds of collections. But the idea is now, as long as we extend this type of variable, we'll see this as we talk about generics, we can now add any set of a collection into our list, starting at a particular index. We can remove all elements from the list. We can query whether the list contains a particular object or not. We can determine whether another object is exactly this list. That's not quite, I should rephrase that. Whether its values are exactly the same, whether its fields and methods are exactly the same. It doesn't have to be at the same address. I could duplicate. Now imagine I can clone students. If I cloned you, you would not be the same person, but you would have the exact same qualities. You would have the exact same DNA, you'd have the exact same, at that moment in time, you would be identical copies of each other. But again, going into the ridiculously violent examples, I murder one of the clones and throw them in a closet, it doesn't hurt you. You can get at a particular index, the value of whatever is at that index. You can see that there's a lot that we can do to a list. If we wanted to make our own list and implement this existing interface, we would have to implement all of this functionality. We would need to have some functionality for each of these methods, which is why we are going to write our own, because we only want to do a subset of this. The most important subset of this. but we still want there to be an interface. So we are going to go make an interface. All right, so let's talk about interfaces in a little bit more detail. They tell us what fields and or methods need to be in everything that implements that interface so that we have cross compatibility. You can think of it like having taken the associated prerequisites for this course. If you had not taken the associated prerequisites for this course, everything that I am saying would be gibberish. But since you all have gone through those associated prerequisites, it still sounds like gibberish. Kidding. You all share the knowledge that you need to be able to understand that. It's very similar in code to say, we're all going to implement this interface. Every one of those classes is going to do the same subset of tasks, although they may do them in a different way. I assign a homework, you're all going to go do that homework, maybe in a slightly different way. So one interface for abstract data type, which means there is one list interface. There are not multiple list interfaces, although there might be multiple list implementations. The array list, the linked list, etc. Because it's abstract, it tells us what the list can do, but not how the list does it, if that makes sense. I give you a homework and I say, go write a linked list. Did I tell you how to write the linked list? No, there needs to be some specification. The linked list needs to contain an add method. The linked list needs to contain a get method. But I'm not telling you, step 1 of the add method, do this. Step 2 of the add method, do that. That is left up to you, and because of that, you end up with different implementations. So the abstract data type, this list, tells us what the interface tells us what the list can do, anything that becomes a list, what an array list can do, what a linked list can do, but it doesn't specify how it can be done. So this becomes a natural link. An interface and an abstract data type are very similar. There's going to be one interface for an abstract data type, and an interface is going to represent an abstract data type. That's not always the case for your code, but if we are dealing with things, something like a list, then there needs to be an interface for that concept. So both array list and linked list implement that interface and have all of the functionality that the interface specifies needs to be there. Last piece of important information, generics. We saw this a little bit in the documentation I just showed you. When we make, we'll go back to an array list. It's probably what we're most familiar with. What goes between those angle brackets? So we have something like that. What does that represent? What does that type mean? Yeah, it can be any variable type. We can make an array list of type integer. We can make an array list of type person, as long as we've defined what a person is within our program. So we can use any existing object that Java knows about, or we can write our own and use them there. Do we think, though, that there is a different piece of code for every type of possible array list? Is the code for array list of integer different from the code for array list of double? Different from the code for array list of person? It's not. We need some way. That would be a lot of code, right? There are an infinite number of objects that I could self-define. If I want to throw them in a list, I need some way of specifying that this list needs to be able to store something, an object type that it doesn't already know about, or to refer to the existing code to be able to get that definition of what that object is. So there is no separate code for each possible data type. We need to define or create a generic type when we write the code. That said, we are going to instantiate this, what we call at runtime. When we run the application, when we make the list, now we are specifying what object type goes in that list. When we write a program, we're talking about the abstract. Here is the process of how this is done. When we actually go run the code, now we are taking that abstract and we're putting something concrete in it. If that makes sense. This array list that can have whatever we want. It's an arbitrary shaped hole. Now we're going to make it an integer shaped hole to put integers in it. We're going to make it a person shaped hole. So we can put people in it. We're gonna, whatever it ends up being. Because we're going to start switching our focus. In prior classes, you've mostly been writing code that you mean to run yourself. Starting in this class, we're going to start writing code that is meant to be run by other people. We are going to be making tools. We're not specifying exactly how those tools are used. We want those tools to be generic so that someone else can go say, this is a great tool. I want to use it to store salaries. And now they can grab our code. We didn't write it to store salaries, but it's generic enough that it can store salaries, however the user has defined salaries. So we're going to start writing tools that are meant to be used by others. So how do we do it? We're going to throw angle brackets on everything that has that particular type of variable. And we are going to, you can put anything in there, but T and or E are the most frequently used letters. The Java documentation uses E. C++'s documentation uses T. So if you see angle brackets and E or T, it's referring to just some generic variable type. You could put anything in there as long as it is an object. You can't put anything primitive in there. So you can't put int, you can't put char, but Java does have these wrapper classes, integer, character, and capital D double, that are objects with the purpose of emulating each of those types. So that's why you need to use the object version of the primitive in order to make it work with something that uses a generic in Java. Okay, so we're actually going to go start with the interface. So I'm going to get up Eclipse. This is very similar to any other IDE that you would be using. So you can see that we have projects. This is going to be everything that we do in here. That was last time I did this. So this is CSCD 300W25. That's going to be our project for the entire quarter. Inside of that, we have an SRC folder, which is where all of our source code is going to go. I'm going to make a new, let's make a package for the moment, and we're going to call this linked list. Inside of our linked list, we're going to be able to now create our classes. And the reason that I'm going to do all of this inside of a package is going to become apparent eventually. So we're going to start with an interface. So you will see whenever you use any IDE, there's a difference here between a class and an interface. We're going to start with the interface. We're going to call this list, and it is going to be our list interface. All right, so now you see the package listed here at the top. So here's where we're going to define the functionality that we want in anything that implements this interface. Now, if we're just coding a linked list, you might question, why do we want an interface at all if we're just making one tool for this? And the reason we want to do this is there are different types of linked lists. We have a singly linked list, a doubly linked list, a circular linked list. We would all want those to be interchangeable, right? Maybe we want to make a singly linked list and swap that out at some point for a doubly linked list, or we want to be able to, they should all be able to do the exact same subsets of things. It's just how they're stored in memory that's going to be different. All right, so what do we want to do for this list? What is some functionality, some basic functionality that a linked list should be able to do? Add. I would even say we probably want a couple different kinds of add. So more specifically, what is one of the types of add that we might want to be able to do?
Add first.
Add first, we're gonna do add in an arbitrary position, and the most frequently used is gonna be add at the end. Like, those are the two we really wanna get done. So we're going to make both of those. Note that we don't specify any kind of public, private, this isn't code. There's no privacy associated with an interface, we're just specifying functionality. We do need a return type for it though. So add returns what kind of, what information would we care to know from an add method? Boolean? Why Boolean and not Boolean?
Just to see if it actually got added or not.
Yes, that's usually the right way to do something that is, it's either going to succeed or it's not. You could make it a void, but then whatever calls the add doesn't know if it ran successfully or not. So we're going to return true or false for this add. And I have made one small thing that we need to make sure that we change. This interface, if we're going to do this, needs to have that generic put in it. So we want to use E or do we want to use T? T? We're going to use T. Again, it doesn't really matter what you throw in there. This T just says it is some variable type. We're doing this as we code it generically, but it's kind of small. Blow this up. When someone uses our code, this T is going to become whatever they need it to be. So add is going to take, let's say we're adding at the end. So we don't really need a position, but what is it going to take? What is the parameter for adding at the end?
Oh,
What is the variable type? It's a T, right? We don't know what it is yet. So we're going to leave it as that generic, whatever this T is, that's also what this T is. If we make a linked list of type person, then the list is of type person. What add takes as a parameter is a person object. That T all represents the same thing for a particular instantiation of this list. But we're writing the blueprint. We're writing how to make a list. So we need to keep it vague and generic. We're going to call this element, the element that we want to add. Question?
Always return true unless we run out of memory.
Unless something happens. So what happens, for instance, if we were to try to add at the end and something will come up. I don't know if I want to get into it quite at the moment. It's, so I will even tell you that it is possible for this to end up with a null pointer exception. What happens if element is null? We'll go there. We'll actually go there. We try to add that at the end of a list. And do we really want that to be the case? Do we want to add a null object to our list?
Okay.
Yeah, all good. So we can actually go, I was going to do this, but we'll actually add in the interface, you also want to list the exceptions that are going to be expected. So we're going to say this throws a null pointer exception. I like to try to think about this as I write the interface as well. What could go wrong when we do this? If you don't think it through necessarily, that's fine. As you write the code and come up with those exceptions, you can come back to your interface and it can be more of a ping-ponging back and forth. What else? The other kind of add should also return a Boolean, but now it's going to take two things. What are those two things? Yeah, we want some kind of index. And the element, same thing. You can imagine that the element here is again null, so we're again going to throw a null pointer exception. There's also something else that could go wrong. What else can go wrong when we try to add a particular index?
Index out of bounds.
Get some kind of index out of bounds exception if the index that we pass it is not in bounds. Are we familiar with the kinds of exceptions that might be useful to be thrown if you give something an index out of bounds? Yeah, that's exactly what we want. We want an illegal argument exception. What else do we want on our list? Yeah, question.
I was just curious, what's the difference between a legal argument exception and index out of bounds exception?
So there's actually no difference really between any of the types of exceptions that you might throw. All this does is tell the user if something happened, what kind of exception was thrown. So from our perspective, we could call this anything we want. When we actually go implement this code, we're going to check index to make sure that it's in bounds. If it's out of bounds, you can write anything as an error message, but it's very confusing as an end user to get no pointer exception value out of bounds. Now I'm very confused about what happened. So matching the exception type to the check that needs to happen is important, not so much for your program's compilation, but for making sure your end user knows what happens when your program crashes. Great question. Whatever functionality we want our linked list to have. Some kind of remove? Sure. What does remove, before we get into exactly what it takes, what does it return? Yeah, we're going to return the value of what was removed in the object that got removed. If we just delete it from the list, then the end user has to save that value before they call remove, and they also have to know that that's exactly what happens when they use your code. If we specify that it returns the actual object that was removed, now the user doesn't have to guess or go, oh no, what happened to my value? I can't get it back now. It was returned. So they could store it in some way that they wanted to without forcing them to write multiple lines. So usually the right way to write a remove is to return the object that was removed. Remove takes what? Yeah, just the index that we want to remove from. We don't need to know what's stored there. We're going to go figure it out. As we remove, what kind of exception do we think we could get?
Legal argument.
We could do an illegal argument exception. We could absolutely do that. There's a little bit of leeway between illegal argument exceptions and index out of bounds exceptions. Usually a legal argument exception is for when the user provides a value that is illegal, and an index out of bounds exception is thrown when the code itself accesses something that is out of bounds. So if you want to try to place blame on the user, throw an index out of bounds exception. If you want to try to place, or sorry, you want to place it on yourself. If it's on the user and it's a parameter, then you should throw an illegal argument exception. It just adds a little bit of clarity. A legal argument exception says it was the parameter that you gave me. An index out of bounds exception is a little bit more generic. Neither would be wrong here though. All right, that's our remove. What other functionality would we care to?
Get.
Add a get. I'm actually going to add a second remove here momentarily, but get also should return the generic object. Makes sense. We're trying to get the value without removing it. So get is going to look exactly like remove does from here on out. Everything that could go wrong with remove can also go wrong with get. Should throw exactly the same exception. If we wanted to overload this remove, what else could we do? What other aspects could we try to, what other functionality could we use with regards to removing something from the list?
You could remove a node based on the element.
Yeah. Yeah, so if we want to remove a particular value, if this is a list of integers, and I want to say, if the number 15 exists in the list, remove the first appearance of 15. We don't know where it's stored in the list, we're gonna have to go search through the list to find it. But that means that when we return, we want to know whether we removed something or not. Now it's less relevant to return the 15, we know we passed in 15. So if we were successful at removing 15, 15 was in the list. If we failed to remove 15, then 15 was not in the list. So we're going to return a Boolean. We're going to call this overloaded remove. It's going to take just the element that we are trying to remove. As we do this, what kinds of exceptions could we run into? Yeah, null pointer exception. If element is null, go find nothing and remove it from the list. Go find this undefined thing and remove it from the list. We don't even want to try to do that. We're going to stop that early and say, I can't do that. Anything else?
I
Yeah,
might want to know what element is in a specific node in the list, so like breaking out items in the list, printing the list.
okay, that would be in the implementation probably when we actually go do this, if we're going to be doing any kind of communicating with the user. That's a good point. We'll certainly keep that in mind when we go implement it. Probably good for now. Other things we want to be able to do real quick before we end class. Let's make sure that we can change the value at a particular place. So we are going to make sure we can update. We're going to take an index and we are going to take the value that we want to change it to. That's going to possibly, when we do this, throw an index out of bounds exception for the index, or a null pointer exception for the element. Any other list, we're going to want to make sure that we can print it out. So we're going to write ourselves a toString. We're also going to keep track of, or be able to tell us the size of the list. We also want to know whether the list is empty. This is everything that we are actually going to go implement in a singly linked list. And rather than fully get started with this, I think we will put that off until tomorrow. But tomorrow we are going to be, for the entire class, trying to get this working. Yeah.
So we could do, the legal argument section for the update as well.
Yes, so an illegal argument would be something like the index, I guess, is, yeah, out of bounds. Yeah, no, you're right. This probably does make more sense than a legal argument, right? I agree with that. I want to be consistent. All right, we will come back to this tomorrow. I have office hours for the next couple of hours. If anyone has any questions about anything we've covered, any updates? Other than that, see you tomorrow.